The last chapter regarding calculus is this one, chapter 9, Differential Equations. It's a very short chapter, just one lesson, in which I will first explain you how to set up a differential equation and then how to solve it. Okay? So first of all, what is a differential equation? Differential equation is an equation that is expressed in terms of the rate at which a quantity y is changing with respect to some other quantity x, and is a function of x, of y, or of both x and y. Mathematically speaking, how do you translate that? You want to do a rate at which y is changing with respect to some other quantity x, so you represent it like this, okay? And is a function of x or y or both, okay? Let's see examples. The idea here is to translate a sentence that is in English into the language of math. That is the idea of setting up the differential equation. In most of the other questions that you will have on this exam, the differential equation is already set up. You usually have to solve it somehow or calculate stuff out of it. You don't need to set it up. This chapter is about, one of the things of this chapter is about setting it up. So let's look at this example. The temperature gradient within a star decreases with respect to the distance to the center of the star at a rate which is inversely proportional to the square of that distance. Find a differential equation. This may resemble something that you learned in Pure Math Say Yes when we talked about the chain rule. There were a particular class of questions that you would always find in exams, and that was already this. You would need to set up a differential equation using the chain rule. So let's look at this. You have a temperature gradient. What does a gradient mean? A gradient means a change. Okay? So how is this temperature changing? It's changing with the distance to the center of the star. So the question doesn't tell you, so you need to figure out symbols to represent both the temperature and the distance. So I picked the usual symbol that is used in physics to represent temperature, which is the theta, and r for the radial distance to the center of the star. So how do I translate this? Temperature gradient with respect to the distance of the center. That's going to be d theta by dr. Let's continue. It is inversely proportional. How do you represent this? If something is inversely proportional, you use a symbol of proportionality and you put 1 over. Proportional to what? To the square of the distance. So I picked r to be the symbol for the distance to the center of the star, so is inversely proportional to the square of the distance. There is here a very important word that I did not mention before, which is the fact that it decreases. So if it decreases, I have to put that mathematically within the formula, and that is done by putting the minus over there. Okay, so here I have the mathematical expression for this sentence expressed in terms of the symbol of proportionality. How do you transform this into an equal? You just multiply here a constant of proportionality. In this case, proportional to what? To minus 1 over r squared. So you just put that k. What is the value of that k? There is no way for you to know this with the information that the question is providing. The next one will already provide you, or already will give you, information that will allow you to calculate that value of k. Let's look at it. It says, the rate at which the velocity of an object decreases as it moves through a liquid is proportional to its velocity. When it enters a liquid, it has a velocity of 5 meters per second, and the velocity is decreasing at a rate of 1 meter per second squared. Find a differential equation. Okay, here you have numerical values. Usually these are used to calculate the constants. Okay, so let's go sentence by sentence, translating into math. The rate at which the velocity of an object decreases. So you have the rate, every time you have the rate with no further detail, it is always in respect to the time. Okay, so the rate at which what? The velocity is changing. So how do you write this? This is going to be dv by dt, okay? Is proportional to its velocity, so symbol of proportionality, proportional to v. I could have put this minus over there. In this case, I opted to stay over here. What is this minus? This minus represents the fact that this is decreasing, as I mentioned before. Okay? So it also says that when it enters the liquid, it has a velocity of 5 meters per second. So when does this happen? Entering the liquid means that the time is going to be 0. That's the starting off time for the situation being described. So when time is 0, the velocity is what? Is 5 meters per second. And the velocity is decreasing at a rate of 1 meter per second squared. How do you write this? The dv by dt is decreasing, so equals to minus 1 meter per second squared. Okay, this is the information that matters. Now you have to find the differential equation. Okay, so how do you transform the proportionality symbol into an equal? You put a k. Okay, now how do you find the value of k? You use the information over there. You know this, that dv by dt at a particular moment is minus 1. And in that moment, what is the value of v? It is 5. So you can find the value of k. K is going to be minus 1 over 5. So now that I know the value of k, I can update this expression and write the final differential equation. dv by dt equals minus 1 over 5 v, or just minus v over 5. See, looking at questions and breaking it down into smaller chunks, that allows you to express those sentences in mathematical terms, will allow you to set up differential equations. Let's look at a third example. The area A of a surface of, the area A of a square of side S is increasing here is important, at a rate proportional to the length of its side S. The constant of proportionality is k. Find an expression for ds by dt. Okay, so let's write down what the question is telling us. You have the area of a square. Okay, the fact that it is a square is important because you know the area of a square. You don't know yet if you're going to need this information or not, but should be in the back of your mind. You know the side of the square is S, and is increasing at a rate proportional to the length of side S. So again, how do you write this down? Area increasing at a rate, so that's dA by dt, that is proportional, similar proportionality, to the length S. So here it is. Again, how do I translate this into an equality? I just put the constant of proportionality, that is k over here. What do I need? I need ds by dt. All the information that the question is giving me ends here, and then it asks me for that, not dA by dt, but ds by dt, which is something that you don't have. So here you should go back to Pure Math AS and learn and remember the chain rule. If you are introduced just on the thing that you are being asked, something that uses an unknown for which you don't have anything to work with, so break it down so you yourself put that unknown there. What do I mean with that? I can put this dA by dt as the product of dA by ds times ds by dt. Chain rule, remember? And this is where the information about the shape of the figure will matter. It is a square, and as a square, you know that the area is s squared, right? So dA by ds, if you differentiate the area in terms of s, you will get what? If you differentiate this in relation to s, dA by ds is going to be 2s, which is over here. ds by dt is the thing that you are being asked. And dA by dt, you just figured it out, is ks. Okay, so ds by dt, the thing that you want is just k divided by 2. Make sense? You have a bunch of questions after this lesson that you can practice just with this. Again, I'm talking about the Access Pro and Access Ultra tiers. But if you're on the Access tier, I also have some exam questions that include the setting up of differential equations. Next section of this lesson is figuring out how to solve them. Okay? You may have two situations. Either the differential equation is in terms of one of the variables alone, let's say x, or is in terms of the two variables. Okay? If it is one variable alone, you already are familiarized with this. So imagine that you have dx by dy by dx equals something in terms of x. You just need to send this dx to the other side and then integrate both sides, right? So the integral of dy will be the y, and this will become a primitive plus the arbitrary constant. And this will give you a set of solutions because of the arbitrary constant that is called the general solution for this particular type of differential equations. What if you have a differential equation that is a function of both variables x and y? This may be solved isolating the terms of x on one side and isolating the terms of y on the other side and then integrating. Okay? So let's say that you have dy by dx equals f of x and y. The idea is that on this function, you isolate the chunks just with x and the chunks just with y. Here, in this particular case, I put it like this. The chunks with x will be the numerator, and then chunks with y would be the denominator. Okay? So I could bring, which one I opted? Okay, I opted to keep everything with y on the left-hand side of the equal and everything with x on the right-hand side of the equal. So this part over here, this part of the mathematical expression that have y's, go to the left. The dy stays in the left. The part over here with x's stay on the right, and the dx goes to the right. And now I integrate both sides. I have here an expression with y's dy, expression with x's dx. I integrate both sides, and I have here an expression, another mathematical expression, which is the primitive of that just with y's. I have here a mathematical expression that is the primitive of this just with x's. I also will have the arbitrary constant. And then my last step is to, on this mathematical expression with y's, isolate as much as possible the y on the left-hand side, pushing everything else that is not y over to the other side. A note, if you have expressions with y squared or y to the power of 3 or square root of y, it's particularly with powers that are natural numbers. You may leave the expression like in terms of y squared, okay? But in any other situations, if you have logarithm of y, if you have e to the power of I, you can perform mathematical operations that will leave the y isolated over here, okay? The end result should be something like this. Okay, again, general solution because you still have the arbitrary constant. You will need extra information to figure out the value of the arbitrary constant. If you are given that extra information, you can plug in over here or wherever that information will fit to get the value of C. If you have a value of C, so everything collapses. This general solution that represents an infinity of different solutions collapses into just one because you will find a specific value of C. So that is called a particular solution. It's important that you know these two terms because you may be asked in exams about one or the other. So let's see here a couple of examples. Find the general solution of this differential equation. It is just in terms of y, okay? So I'm going to send this to the left-hand side, send that to the right-hand side, okay? So if this goes to this side, you'll have dy divided by e to the power of minus y, which is basically just e to the power of y dy. You are left with 1 over there, this dx goes over there, and you have then this. And now apply the integral on both sides. And the integral of this is just e to the power of y. Integral of the x is x plus c. Again, you have to leave the final answer in terms of y, so you do natural logarithms on both sides. Natural logarithm of e to the power of y is just y, and this side is going to be just natural logarithm of x plus c. Another example, this one. This one is already a differential equation in terms of x and y. So what am I going to do? I'm going to send the y to the side, so you have 1 over y dy. I'm going to send the dx to the other side. I will just have x dx. And now I have everything with y's on one side, everything with x's on the other side. Integrate both sides. This will become that. This will become that. I don't want the final expression in terms of natural logarithm of y. I want it in terms of y. So now I do the opposite of what I did before. I apply the exponential function on both sides of the equation. So I'll have e to the power of natural logarithm of y, which is the y that I want. And on the other side, I have e to the power of that expression. I could put plus c, but that will mean times e to the power of c, which is itself a constant. Okay? So I can write just the final answer as the constant times e to the power of x squared over 2. One final word for situations in which you are asked to verify that an expression is a particular solution of a differential equation under certain conditions. So what you need to do, you need to use the expression that you are given to do the proper substitutions on both sides of the differential equation. And after doing that on one side and getting a result, after doing that on the other side, getting a result, if these two results match, then the expression is a solution. You also need to plug in the conditions on the solution to see that they match too. This is a simple part. Okay, so an example. Show that sine of y equals x is a solution of the differential equation dy by dx equals 1 over square root of 1 minus x squared. Okay, so again, what is the first step? Use the expression, this one, to do the proper substitutions on both sides of the differential equation. And you may need to operate mathematical steps in order to do that, so that you'll eventually end up with two expressions that should be the same. Okay, so I'm going to start with this one. So what do I need? With this, I need to perform here mathematical operations that will eventually lead me to an expression of dy by dx. I have two options. I think that the simplest one is the one on the bottom, so I'm going to focus on that one, but they should both lead to the same result. I start with this. I want to get from this dy by dx. So the thing that is simpler to me is to differentiate the function, not in terms of y, not in terms of x, like the example on top, but in terms of y. So I differentiate in relation to y both sides. That's what I did over here. I just swapped the position. So I have dx by dy equals d sine of y by dy. If you differentiate this in relation to I, what do you get? You get the cosine of y. So if you know that dx by dy is the cosine of y, if you flip it, that's what I want. I want dy by dx, not dx by dy. If I flip it, I know that dy by dx equals 1 over cosine of y. So I've worked the expression that I was given so that I could get the left-hand side of the differential equation. The dy by dx is this. If I now use this expression on the other side, and I will still get that, then I prove that that it may be a particular solution. So let's do that part. Now, focus on this. And you need to do something over here that using this expression, using this expression, to try to find something close to that. So what is the only option basically here? Is substituting this x by sine of y. So that's what I did. I put it over here. 1 minus sine square of y is cosine square of y. Square root of cosine square of y is just cosine of y. And see, these two match. What is the last and simplest step? See if the plug in the conditions on the solution, the one that is being given, to see that they match too. What is the conditions? When y equals 0, when x equals 0. So let's figure out if this is true. When x equals 0 means what? You plug 0 over there. When is sine of 0, 0? That happens when y equals 0, which is the condition that you have there. So this also match. So these two things are obey the conditions required for the expression to be a particular solution to this particular differential equation.